Alright, so today we're going to be talking a little bit about electricity. And the mathematics behind electricity. So the idea is that if we're thinking about electricity, I mean we've got electricity running through our light bulbs, our computers and things of that nature. We want to know what's going on the mathematical side of things. So one of the first things to kind of realize is that electricity is something that kind of runs through some type of circuit. We're going to be talking mostly about electrical circuits. To understand electricity, one of the best ways to do that is to kind of think about what electricity is at an atomic level. So if we look inside the atoms, we have protons, we have neutrons, and we have electrons. Now the protons and the neutrons are kind of sitting in the center of the atom, and outside in an orbit we've got electrons. As the electrons orbit the atom, one of the things that can happen is that some of the electrons can be free. And what it means to be free as an electron is you're able to move from one atom to the next. Now, atoms that are made up that are part of a material that allow that free movement are typically what we call conductors. So if the electrons are able to move, then it's going to be a conductor. And if you're not able to move through the material as well, we would call it an insulator. So when you think about conductors, you're going to think more like copper or metal. So if you look inside a wire, a lot of times you end up seeing copper. Do not cut open some wires to see, but copper a lot of times shows up on the inside. And insulators, what you see wrapped around the wires, typically like some type of rubber or plastic. So the idea is, if the atom is part of a conductor, then the free electrons are able to move much more readily through that conductor. Why would they move? Well, it turns out, if you're looking inside an atom, some atoms have more electrons and some atoms have more protons. So if you have more protons than electrons, we give that a positive charge. We say that it's a positive charge. And if you have more electrons than protons, we call that a negative charge. So then the idea is that nature typically likes balance, and so if we've got more electrons than protons, we've got a negative balance, but our electrons are able to move, and if the atom's sitting next to an atom that has more protons than electrons, we kind of like balance it out by letting the electron move from one atom to the next. So electrons are going to move from a negative charge to a positive charge. Now the way that they do that is they do it through a conductor. So if we have some stream, some line of conductor for those atoms to be moved on, where on one side of the conductor we have too many electrons and on the other side we have too many protons, then the electrons will move through that conductor from one side to the other. So the idea is that essentially you can imagine almost like having a battery, and on the negative side we've got more electrons and on the positive side we've got more protons. And now if you connect a wire to the back of the battery and maybe hook up a light bulb to the other side, and then allow that electricity to flow back to the positive side, then we end up having that the electrons will move through this conductor all the way to the positive side of the battery. And that's pretty much how electricity ends up working. The electrons are moving through what we call an electrical circuit. So we call this an electrical circuit. Now, the electrons only have one path to follow in the circuit. So we're going to call this a series circuit. Sometimes there's more than one path to follow. We would call that a parallel circuit. So suppose that you have a battery. Here's the negative side, here's the positive side. Maybe it can flow this way through, let's put a light bulb on there. And then maybe it can flow through this way, and let's put another light bulb on there. We would call this a parallel circuit. And a parallel circuit is when the electrons have more than one path they actually follow. We're going to start talking about series circuits, but we'll bring in parallel circuits as well. But the primary thing that we want to look at is how the electricity flows and how quickly it flows and things of that nature. One thing you might be wondering is why I keep on saying that electricity is flowing from negative to positive. It kind of depends on who you are when you're thinking about electricity. Are you someone that studies the more scientific side, or are you someone that's actually like an electrician? One of the things that ends up happening is the electrons are moving from negative to positive, but then people like to think of the electrical charge as moving from positive to negative. So if you've heard that electricity goes from positive to negative, that's true in one sense. You can think about the fact that the electrons are moving. The electrons are physically moving, but in some sense that means that the positive charge is actually moving as well. Because as the electrons move, they increase the number of electrons over here, so there's less positive charge and it has to move in this direction. So we end up having the electricity in some sense kind of moves both directions, but in this sense we're really talking about the way the electrons move. Another thing to kind of notice is that right here we're talking about direct current. Direct current means that the electrons are moving in one direction. You can almost think about electricity as like that friction that's caused by the movement. So direct current makes it move in one direction. On the other hand, if you think about it like a friction type of thing, it would be friction if I just went back and forth really fast. So if you can imagine, the reason a light bulb lights up is because the electrons are moving through the filament in the light bulb, the old-fashioned ones. If we move in one direction, it causes that friction and allows it to light up. But if we were going back and forth through the filament, we would still cause a lot of friction and it would light up. That's what we call alternating current when it goes back, back and forth. So we'll talk about direct current, but there are alternating current. There's alternating current as well, which is something interesting to kind of take a look at, but we'll focus today on direct current. Okay, so now that we have the circuit, we'd like to talk a little bit about the characteristics of electricity. So there are three numerical characteristics. The first one is current. Current is the speed at which the electricity flows. It is measured in amperes. And we denote it amps. So if you ever see that something has this many amps, that's how fast the electricity flows through that item. The second thing that we can characterize with a number is voltage. Voltage is kind of like the difference between the number of electrons on one side and the number of electrons on the other side. We kind of almost think about it as like the pressure, electrical pressure. And that's measured in volts. And then the last one is what we call resistance. Resistance is how much the material resists the flow of electricity. And we measure this in ohms. We denote it with so this capital gamma, so what we call it ohms. And what ends up happening a lot of times is you might see a K in front of that, and this would mean 1,000 ohms. So if you see like 4K, so 4K ohms, it'd be 4,000 ohms altogether. The reason why we have the flow resisted is it depends on the material it's flowing through. There are things called resistors. So if you want to see a resistor, I've actually created a little circuit right here. The resistor is like this little thing that looks like a tube, and it actually resists the flow of electricity. But there are other things as well that kind of resist the flow of electricity. So for example, light bulbs. Light bulbs, the old-fashioned ones with the filaments, those would resist the flow of electricity. So resistance is actually just the slowing down. One of the things that happens when we're talking about a circuit is we like to think about a circuit kind of like pipes of water. It allows us to kind of visualize what's going on. The current is how fast the water is flowing through the pipe, or the garden hose. The voltage is how much water pressure you have. How high is the pressure? If you've got low pressure in your shower, water barely comes out. If you've got high pressure in your shower, water comes out really fast. The resistance is kind of impeding the flow of the water. So it'd be like rocks in the line, right? So if I have a garden hose that's full of rocks, the water's not going to flow very quickly. Now, if I have an increase in voltage, suppose I have some resistance, so like some rocks in the garden hose, and so there's my resistance, and I've got a low voltage, so there's not very much pressure, and I turn it on, water trickles out. But as I change these numbers, I would expect that there would be changes in the other numbers associated. So suppose I keep the same rocks in the garden hose, same resistance, but I increase the voltage, increase the water pressure. When I do that, it won't be a trickle anymore. The water will flow a little bit more quickly because the voltage or the pressure has increased. So in other words, when we're thinking about electricity, as the voltage increases, the current should increase. As the voltage decreases, the current should decrease, assuming that the resistance is staying the same. If the voltage stays the same and the resistance increases, then that should slow down the current. We're impeding it more, so it should not be able to flow as quickly. So these numbers all have some type of relation, and that relation is what we call Ohm's law. And Ohm's law is a law that basically tells us how these three numbers are related to each other. Ohm's law is really a formula, and it tells us that if I is the current, measured in amps, and V is the voltage, and R is the resistance, then Ohm's law tells us that the current is equal to the voltage divided by the resistance. So it tells us how these are related. So that's the reason why if the voltage increases, the current increases, assuming that the resistance stays the same. So if this number gets bigger, this number has to get bigger. If the resistance increases, then this whole number gets smaller, so then the current would get smaller, assuming that the voltage stays the same. Those three numbers have that kind of relationship. So here's an example. So if you're looking at a 100-watt light bulb, we know that a 100-watt light bulb has a resistance of 144 ohms. Actually, we don't all know that. I just looked that up on Google. And then if we connect the light bulb to a circuit with 120 volts, like in our house, we can ask what's the current. Well, according to Ohm's law, the current would be equal to the number of volts, 120 volts, divided by the resistance, 144 ohms, and that would give us a current of 0.833 amps. So that's how fast the electricity would be flowing through that light bulb. Now, given any number, you can actually, any two numbers, you can always figure out the third. That's because I equal to V over R is the same thing as V equal to IR. So if you know the current and the resistance, you can compute the voltage. So for instance, suppose you want to make sure that the electricity is flowing at a certain current, and you know how much resistance is on the line. You can figure out how much voltage you need in order for that to work. And then you can also do that the resistance is equal to the voltage divided by the current. So suppose that you know how many volts are in your house line, like 120 volts, and suppose that you need the current to be a certain number, then you can figure out how much resistance to put on that to make sure that it doesn't flow any faster. Why would you not want it to flow faster? If the current's going too fast, it might blow it up. Like if it's a light bulb and you got too high of a current, the light bulb's going to pop. So you might want to make sure that you put resistance on the line. And oftentimes, if you were to actually open up, don't do this, if you were to open up like an LED light bulb, you'd actually see some resistors in there to make sure that it doesn't just pop. And so that's so those types of things end up having this interplay. All right. So I want to kind of show you what we're talking about in a little bit more detail. And so I want to show you that I've made a circuit, and my circuit has a couple of features. So what I've got here is I've got a 9, so my circuit I kind of showed you earlier has a 9-volt battery. So there's a 9-volt battery. And from the battery it goes up. I can kind of show you where it happens. On this battery, if you follow the black line, it goes into what's called a breadboard. On the back of here there's a bunch of wires, and I know where the wires are at so that I know that it goes through the black line, and then it connects from the black line through the purple line to the switch. So there's a switch right there. So this is the switch. The reason why it's a switch is because right now it's open. It does not allow the electricity to flow through that switch. If I push the button, it actually closes this, makes it shut, and once it shuts, it allows the electricity to flow. The electrons are able to flow through the conductor. From the switch, it runs through an LED light bulb. So here's an LED light bulb. And then from the LED light bulb, it runs through a resistor. And the resistor that I have on it right now is 10k ohms. And then from the resistor, it runs back to the battery. Now, when I push this switch, what will end up happening is the electricity will actually flow and it will turn the light on. So I don't know if you can see that, but the light is on, light is off, and so on and so forth. You can see the light's being turned on. So now if I want to figure out how fast the electricity is flowing through this, I can do some mathematics. Before I do this, I have to point out one really pesky thing about LEDs. So the running from the way that the water or the electricity flows through the circuit, each path is called a series. So this is one series. That's why we call it a series circuit. In a series circuit, the LEDs kind of act like resistors, but they're not exactly resistors. What they do instead is they drop the voltage by 2 volts. Each LED drops voltage by 2 volts. Not as a resistor, it just simply drops how much voltage is flowing through. Now there's a lot more scientific explanation for what's going on, but this is pretty much one way to describe what's going on. It drops the voltage by 2 volts. That's for each LED in a series. So if I added another LED light bulb, it would drop the volts from 9 volts 2 times. 2 volts down to 7, 2 volts down to 5. But either way, each LED drops the number of volts by 2 volts. So what ends up happening then is on this series, so over here, we actually have 9 minus 2, 7 volts, because there's an LED light bulb on there. We have 10,000 ohms, and from those two numbers I can figure out the current. So the current is equal to, so I is equal to V over R, it's equal to 10,000 divided by 7. And if I take my calculator and take 10,000 divided by 7, I get 1428.57. And that would be the number of, oops, totally screwed that up. So I is supposed to be equal to V over R. I put the R on top and the V on the bottom. It's supposed to be 7 divided by 10,000. that'd be way too much current. That light bulb would definitely not exist anymore. 7 divided by 10,000. 0.0007 amps. And so one of the ways to describe this is just to call it 0.0007 amps. Because a lot of LED light bulbs have such low currents, a lot of times we'll go to the nearest thousandths. So this is tenths, hundredths, thousandths spot. So this is 0.7 thousandths of an amp, and we call that milliamps. So if you ever see 0.7 milliamps or MA, that's talking about how many thousandths of an amp it is. So this light bulb has a current of 0.7 milliamps. I want to show you a slightly different thing. Is if I change this right here, this resistor from 10 kilo ohms to 330 ohms, what would end up happening is I would replace this 10,000 by 330. So I play the exact same game, but now it'd be 330 amps, 330 ohms. And so the current would be equal to 7 volts divided by 330. And if I take 7 and divide it by 330, I end up getting 0.021, 21, and so on and so forth. And that's how many amps it would be. Now if I move this over tenths, hundred thousandths, this would be 21.2 milliamps. That is way, way, way larger than our previous one. Now I just so happen to have it set up so that I can quickly change this and run it through a different resistor. And this new resistor has 330 ohms. So this is the new resistor. That's what the light bulb looks like. But if I go back to the old resistor, it's much dimmer. So the idea is that if I increase the current, the electricity will flow much faster and it will have a brighter light bulb. Now, one of the things that I could do is I could have instead, so right now I've got one LED light bulb on this. So what I could do instead is I could add a second LED light bulb. So I've got a second LED light bulb over here. And I'm just going to throw that second LED light bulb into the circuit. And this will allow me to see that because I've got two light bulbs on here, I won't have it nearly as bright. So I've got two light bulbs versus if I just had one light bulb. That light bulb, you can't really tell too much, but it's a little bit brighter than when I was running both light bulbs. And the reason for that is because now if I had two light bulbs on here, so I put another LED on here, what would end up happening is instead of having 7 volts, in this series I now have two LEDs. And so my number of volts would be 9 minus 2 minus 2. You have to subtract 2 for each LED. This would be 5 volts. And in that one that I just showed you, I actually had 10,000 ohms. And so if I take this, the current is equal to 5 over 10,000, which is 0.0005, or 0.5 milliamps. So it's 0.0005 amps or 0.5 milliamps. Now the difference between 5 milliamps and 7 milliamps, not that big of a difference. In fact, you might not even have been able to tell that one was lighter than the other. But it was. It was a little bit dimmer than the other one. So this is what we have for series circuits in the Ohm's law.